100%. Thank you. All right, so today we were talking about radioactive dating. So Friday we talked about how you can predict how much of something will be left after a given amount of time. You know the rate at which it decays. Today we're going to do the opposite. We're going to say if we know how much of something we started out with and we know how much there is now, we can use this to determine how much time has passed. Right? This is how carbon dating works, and uranium dating, and different types of dating depending on the time period and so on. So with carbon dating, we know how much we start out with because we know that all living things have the same percentage of... Let's shut that, please. It's embarrassing. It really is. I don't know. So we know that all living things have the same percentage of carbon-14 because we all take in carbon, right, when we eat sugar and fats and things like that, and a certain fraction of that carbon is carbon-14. And so as long as we're alive, we're going to keep taking in carbon, and we're going to maintain that proportion. But once we die, we stop taking in carbon, and so the amount of carbon-14 in our body decays over time. And so we can use that to date things. So we know the present amount, we know the original amount, what we don't know is time. So we're going to take the equation from Friday, and we're going to solve that for time. So here is our original equation. P equals A times 0.5 to the power of T over T half. All right, so if you take a moment to look at this, we're trying to solve for the T up here. This is in the numerator of the exponent. So it's not just regular algebra. This is kind of nasty because it's in the exponent. We're going to have to do a little bit of fancy work here. All right, first thing we're going to do is get rid of this A. So let's deal with that. We divide both sides by A. So that goes away. So we get P over A is equal to 0.5 to the power of T over T half. So now, the next step that we're going to do, and it may not make sense to you why we're going to do this, but what we're going to do is we're going to take the log of both sides. So if both sides are equal, and you take the log of both sides, they're still equal. Don't worry about why we're doing it. We're just going to do it. So natural log of this side, natural log of this side. Right? They should still be equal because they were equal before. So that's fine. Now why did I do that? But here's the thing. We're trying to get this t out of the exponent so we can solve for it. And there's this rule in math that says this. So this is kind of a side here. If you have log of, say, x to the y, that's the same as saying y times log of x. So it's one of those funny log rules. Logs have a lot of funny rules. And this is really useful to us because this y is what we're trying to get out of there. In this case, it's t. So we're going to use this rule here, and we're going to rewrite this left side, taking this exponent and putting it out there. That's what the logs allow us to do.
What is that?
Which one?
But it does not look like letters.
Here? ln.
LN?
ln.
Okay.
Yeah, I can rewrite it.
How
Just
did ln go from log?
natural log. We could use the different log if we wanted to. We're just using that log. It doesn't matter which log you use. The rule is always the same. Okay? All right, so from here, we're going to take the exponent and put it out in front. So now we're going to rewrite it like this. Left side doesn't change. P over A is equal to, and so this whole thing comes out. T over T half times ln of 0.5. So all we did was we took the exponent, we threw it out in front. We're allowed to do that because of this rule. Remember, the whole goal here is to solve for t. We want to be able to solve for time so we can plug in numbers and date things, right? All right, from here it's just algebra. We can finish up. We're going to divide both sides by ln of 1.5. Cancels on this side, right? That's all gone. And so we get P over A 0.5 is equal to T over the half-life, T half.
Wait to do this for every problem?
No, once we solve it, we have our solution, we just plug in numbers. Last step is multiply both sides by t half. These cancel. And so your final solution here is t half natural log of p over a over natural log of 0.5 is equal to time. There we go. We solve for time. So all we need to know is how much of the substance we have now, how much there was originally, and what the half-life is. We can plug numbers in and find out how old that sample is. This is how radioactive dating works.
So you just have to log on our calculator.
Yeah, you can either use natural log, ln, or you can use the log button. It wouldn't have mattered if we had solved it using regular log. Just use the same for top and bottom. All right, we're going to do an example problem, so don't worry.
So don't erase anything yet.
You are late.
Okay. You don't want me to get your notes?
You don't require you late.
We were running the mile, Jim.
That's terrible. Well, I got to do a problem here.
Well, can you hold on?
All right.
We still have 40 minutes left to do it.
All right, I will wait 2 minutes for you guys. Lucky I like you. All right, I want to make a space in here to write. That's where our problem's going to be. All right, so let's say, what's up? Welcome, welcome. All right, everybody's coming in late. I'm gonna have to wait now.
So ln is log?
Yeah.
What's
All right,
gonna
listen,
be in my
everybody who
calculator?
came in late, write this equation down here. Forget the rest of it. I don't want to spend a half hour because I'd have to re-explain everything. Just get that down when you get a chance, and then we'll go ahead and do a problem. So to recap for everybody, we're talking about radioactive dating. So we're taking the equation we had Friday, which told us how much of something will be left after a given amount of time, and we solved that equation for time. That there. And so here's the solution. And so we can use this if we know how much amount we started with and how much we have left and what the half-life is. We can use this to find out how old something is. So this is how carbon dating works and things like that. So I'm going to do a problem in a second, but this is the equation you need. This is the solution.
What are those two letters that they want?
ln.
LN?
ln, which is natural log, is a function of the calculator.
Is our calculator going to say ln or are we
It'll
gonna
say
have
ln. And again, I just needed to use any kind of log, so had I used the regular log, this would have been fine also. It just had to be the same on top and bottom. All right, so everybody's got that written down. Then I'm going to do a problem here. Okay, so what do we have here? If a sample of that should be a dead organism, right?
Do you have white out?
No. Sample of a dead organism has 200 grams of carbon-14. And we know it originally had let's say 1,800 grams. How old is its
Half-life.
right? So half-life of carbon-14 is 5,730 years. So this would be like how you would date like a saber-toothed tiger or Neanderthal or something like that. Couldn't use it for dinosaurs because the half-life being 5,000 years, there wouldn't be anything left after 50 million, 100 million years. So it doesn't work for things that are that old. We need to use some other sort of dating. All right, so let's find some space here. So let's list our givens. We got our half-life. The amount that we finished with, this is the present amount. So this is your P, is 200 grams. The original amount was 1,800 grams. Okay. And that's all the information we need. So now we can plug it into this equation. So what we're going to write is 5,730 times natural log of P over A. So it's 200 divided by 1,800. All that, natural log of 0.5. Got it. And I'll wait for a minute because I know some of you are still catching up. All right, keep moving if you have to. You can take a seat here, whatever you want. All right, so when you get to the stage of plugging this into your calculator, you're going to plug in this fraction first. 200 divided by 1,800. You're going to hit the equals button and get an answer, and then you're going to take natural log of that answer. Then when you get that, you're going to multiply by 5,730. So do it in that order, it won't screw up. Otherwise, you're going to use a ton of parentheses. And then you got to divide that by natural log of 0.5.
How'd you get the half years?
This is a constant. I told you it's carbon 14. So you just look it up on the table. Carbon 14's half-life is 5,730. All right, so did anybody plug this in yet?
Yeah.
What do you got?
18,163.67 grams.
18,163 years. Anybody else get that? Anybody else plugged in yet? Everybody's still ready. All right. You got that too? All right. 2 people got it. It absolutely must be right.
Well, shouldn't it be 64 and 6.6?
Oh, is it? Questions? Do I need to do another problem? Okay. Does everybody know what we're doing? Okay.